Today I'll be going over drawing Bode plots by hand. I'll just be doing an introduction to the matter. So there are a few good reasons to draw Bode plots by hand, chief among them being building an intuition for transfer functions. So some of the things that drawing Bode plots by hand will teach you will be how to look at a transfer function and then directly evaluate both the bandwidth and the stability margins for your system. You'll be able to instantly view how to add in poles during controller tuning and what that'll do to your system. And you'll be able to see which frequencies that pass through your system are being blocked. So Bode plots are pretty simple, but they were developed in Bell Labs by, I believe, Hendrik Bode, and he did it for the kind of quick system analysis that we'll be wanting to do here as well. And so a Bode plot consists of a magnitude plot and a phase plot. It's most often drawn with the x-axis being on a log 10 scale of radians per second, and on the y-axis with either if it's a magnitude plot, it's going to be in linear decibels, or if it's the phase plot, the y-axis will just be in degrees. It's important to note for the Bode plot that when we draw these by hand, they are approximations. You'll see that we will draw with sharp corners today, and that is an approximation. Those sharp corners don't exist in better representations of the Bode plot, and usually in computer-generated methods, you won't see those. But for our approximations, they'll work, and usually they can work quite well, and I'll discuss later on when the approximation doesn't hold up very well. So here's what the Bode plot looks like, just as I mentioned on the previous slide. This is what we'll be putting our transfer function onto. So if we have a transfer function, what we want to do is we want to isolate the zeros and the poles. And we also want to make sure that we understand what are, in our isolated zero and pole transfer function, what the different components mean and what they look like on a Bode plot. So a constant gain, or a DC gain, in our transfer function will look like a flat horizontal line on the magnitude Bode plot. The integrator will be a straight line going down. The differentiator will be a straight line up. And a simple pole is flat and then slopes down, while a simple zero is flat and then slopes up. And we'll provide an example now of a transfer function so we can see what this looks like. So I'll say that we have the following transfer function here, and we've already gone through and we've isolated the zeros and the poles, and so this is the transfer function that we'll be working with. We're good to get right into sketching out our Bode plot. So we can see from the previous slide that the DC gain is 2, and we'll recall that that is represented as a straight line or a flat line on a Bode plot. And so this is what it would look like. On the magnitude plot, the line will be at, I say hertz there, but it's in 6 decibels, which will be 20 times log 2. And we can see from the zero of the transfer function that at frequency of radian per second equals 2, it will slope upwards. And we also see from the pole of the transfer function that it will start to slope downwards at omega equals 10. and those are both in radians per second. And so we plot those out for first the 0 line. And so for our 0 and the magnitude, we see that we go up until it's flat until omega is at 2. And something that you'll notice here is that I've included the DC gain here. There's no need to do that. That's just idiosyncrasy of mine. You can draw it straight from 0 because we've included the DC gain earlier. But if you want to just include the DC gain moving forward, you can draw it like this, like I've done here. And then for the phase plot as well, we'll see that at omega equals 0.1 is when it starts to slope. And we see that it rises at 45 degrees per decade until it reaches 90, after which it's a flat line. And for the pole line, it's similar. On the magnitude, we can see that I'm starting off at the DC gain that we had found previously, and then it's sloping down at omega equals 10, which we had looked at before, and it'll slope down negatively since it is a pole. And for the phase of that pole, we can see that it is 0 up until omega equals 1, and then it decreases at negative 45 degrees per decade until it hits negative 90 degrees at omega equals 100. And so now all that we need to do to finalize our Bode plot is to just superimpose those 0 lines and those pole lines on top of each other. We sum them up and then we put them in the plot. And so we can see here that for the magnitude, because I've already included the DC gain in both of them, I want to be a little bit careful. You don't want to double add the DC gain there. Once again, that's just an idiosyncrasy of mine. So the DC gain stays at what we initially found it, which is sort of the 0 reference that I've set. And then it'll climb up from omega equals 2, which we saw with the 0, and it'll keep climbing up until the pole wakes up and starts acting at omega equals 10. And then afterwards, the slope on both of them will cancel out and create a flat line. And we'll sort of see like an increased DC gain then at those frequencies greater than omega equals 10. And so then for the phase, it's a little bit different because our phase 0 line topped out at 90 and our phase pole line bottomed out at negative 90. But it's the same idea where we go through and we will sum up the 2 of them, and there we've created our Bode plot. And so it's fine to have a Bode plot, but we'll touch a little bit on what some of the interpretation is for that Bode plot now. So what the magnitude plot really is saying is it's telling us what the gain is between the input and the output of our transfer function. And so what we see is that a positive decibel result would be amplifying the vibration that's being passed into the system. And a negative decibel result would be dampening. And then the phase plot represents how responsive our system is to inputs. So a positive degree value would mean that our system is predictive, which means that it is changing based on the rate of change rather than like a position data point. And a negative degree value would mean that our system is lagging behind. So that the output will significantly lag behind the input. And if it is 0, then the input will instantaneously match the output. And so now we're going to look at an example with our given example transfer function of, let's say that we've got some motor that converts a 1-volt signal into 1,000 RPM. And for our case, we'll say that we want to pass into that motor through our system a sinusoidal signal of 1 volt and a frequency of 7 hertz. All right, well, we've got here our Bode plot. So what can we do here? We can draw our line right at 7, and we can go across and start to figure things out then. But no, we can't, because the x-axis is not in hertz here. This is a stumbling block for almost every undergraduate control theory course, and it's very important to remember that the x-axis is not in hertz, it is in radians per second. Fortunately, it's a very easy conversion between the two of them. It's just 2 pi times the hertz value, which in our case is 7, which is roughly 44 radians per second. So now we can take that and we can look at our results. Something that's important to note when we are looking at these Bode plots is because we've drawn them by hand with these sharp corners, they are approximations. And so what that means especially is you want to be careful when using values in a hand-drawn Bode plot that are close to the corners. So if you're somewhat close to a corner, or if you have many corners, because you've got a whole bunch of different zeros and poles, it probably wouldn't be recommended to use a hand-drawn Bode plot. But for our case, in our example, I've structured the question such that it'll be okay. And so now we'll convert from our decibel magnitude that we're about to find on our Bode plot to our gain using the following formula. And then we'll also convert from on our Bode plot location on our phase plot to getting our time shift in our input and output via the following formula. And so going over to our 44 radian per second frequency, we can draw our line across and see what our results are. So for our magnitude plot, that's roughly 22-ish, and I know I haven't drawn it very neatly there, but it's roughly 22-ish. And then for our phase that we have here, it's going to be close to around 10 degrees. And so one of the reasons why the hand-drawn approximation works here is that if we look at the magnitude plot, it's sort of where we're well past where the corner is, around 10 radians per second. And if you look at the phase plot, we're close to being, in the middle between the phase, between the corners at omega equals 20 and omega equals 100. And so we can take those formulas from the previous slide and we can convert our values. So it ends up working out so that the gain is going to be somewhere around 9-ish for our magnitude, for our DC gain. And then that the phase will end up corresponding with a lead time of around 4 milliseconds. And so then we can take that and we can use it to convert into RPM with the motor, and we can see how the motor will react to that signal when it's passed through our system and then into the motor. And so in the description for this video, I've included some very good resources, including some practice problems from Swarthmore College. And I'd recommend looking through those and through some of the additional videos as well.